Recording in progress.
Well, good morning, everyone. Hope you're having a good day today. It's a beautiful sunny day here in California. Yesterday was kind of cloudy, but today looks great. Good morning if you're watching on Zoom. Good morning to people on YouTube. It's good to see you today. Hey, we're going to continue our discussion today of finite state machines. We're going to talk more about non-deterministic finite state machines, how to convert them to deterministic ones, and we're also going to introduce a new concept, which is NFAs, non-deterministic finite state automatons with Epsilon transitions, how to convert those as well to deterministic ones. And that's going to lead us into a final concept or skill, which is how to turn a regular expression, any regular expression, into a finite state machine, which you can then implement in a computer program. So we kind of got almost all the pieces together. We have how to turn a finite state machine into a computer program. I showed that to you about a week and a half ago. And then also we are learning how to convert an NFA to a DFA. We have to introduce or put in the Epsilon transitions and then show you what are called Thompson's constructions to convert a regular expression into an NFA. And then there you can go to a DFA, and there you can go to a computer program. So essentially it's a little mini compiler. It takes a regular expression and compiles it into a data structure and then executes it. So I'll kind of show you all the steps. We're not actually going to write a computer program to do that, but it's all the basic steps. And then finally, we'll wrap up with our last programming assignment for the semester, which is one in which you're going to use regular expressions to do pattern matching on some files and pull out things like email addresses and phone numbers, zip codes, words, variable names, comments, things like that. And that'll become after the break. So let's get started. I have here an NFA. We need to transform this into a DFA. But the first question to you would be, why is this an NFA? What gives it away? What characteristic does this finite state machine have that makes it non-deterministic? So you look at the states, you look at the transitions, and you see, what do you see in there that makes it so that at some given point in processing a string, you don't know what to do. You don't know whether to go this way or that way. So what we're looking for here is at least one state, and there's two in this case, at least one, where there is an ambiguous transition. There's one here at state number 2. You could either take this transition or this one if you found an A. If you're on state 2 and your input symbol was an A, you could either take this transition or this one, and you wouldn't know which one to do unless you could look ahead at the next symbol. And then state 3 as well also has an ambiguous transition. You could either take this or this on a B, and again, you wouldn't know which one to do unless you could look ahead at next symbols. Okay, so let's get started transforming this into a DFA. Remember last time we had that analogy of using an explorer who's exploring a cave system, and you've got a map maker, and the two really kind of can't see each other. All they can do is communicate about what they see. So the cave explorer starts in room number 1 and looks to see what transitions are available and sees an A and sees a B. So we know that there's 2, one labeled A, one labeled B. If you follow the A transition, you'll end up in room number 2. And if you follow the B transition, you'll end up in room number 3. So let's explore room number 2. So if you're in 2, what transitions do you see? Well, you see a B, you see an A, and you also see an A. So there's an A and a B leading out. Where does the A go? Well, if you followed A, it would take you back to 2, and it would also take you to 4. So following an A transition out of 2 takes you to 2 and 4 at the same time. So that's a new state, and we'll label it 2 and 4. What about B? If you're in room 2 and you follow the B transition, where do you end up? There's only one B coming out. Where does it go? Good. It goes to 3. Now, let's turn our attention to, let's do 3 next. So in 3, what transitions do you see? Well, there's no A, but there is a B and a B. So there's only one B coming out of 3. And where does it go? Oh, we got a whole bunch of people on YouTube that are typing in their answers. Good. So B goes to 3 and 4. Akash, Lord, Marylori, and self-described all said the correct answer. So B from 3 goes to 3 and 4. Okay, let's go back to 2 and 4. So here you look at 2 and 4, and you say, what transitions do I see? Well, out of 2 and 4, I see an A, I see an A, and I see a B. So I know there's going to be an A and a B leading out of 2 and 4. But where do they go? So out of 2 and 4, where does the A transition go? So one goes to 2, and another one goes to 4. So if you were in rooms 2 and 4 at the same time, and you followed the A corridor, you'd end up back in rooms 2 and 4. So this one goes back to itself on A. Kind of strange, huh? What about for B? If you're in 2 and 4, and you follow the B, you end up only in 3. Let's try that same thing for the other state, 3 and 4, the one we haven't done yet. So if you're in 3 and 4 at the same time, you see only a B transition, but where does it go? If you're in 3 and 4 at the same time, and you follow the B transition, where does it go? It goes back to 3 and 4. So this one loops back to itself on a B. So at this point, we have completely mapped out the NFA, converting it into a DFA. We followed all the transitions we can. There's no new states to add to the map, so we are done. The last thing we need to do is to mark what are the accepting states. So you look in the NFA and you see that 2 and 4 are accepting states. So any state with a 2 or a 4 in it is going to be an accepting in the new map. This one will be an accepting because it has, well, both a 2 and a 4. This one is an accepting because it has a 4, and this one is an accepting because it has a 2. So that should be our deterministic finite state automaton. But the last thing to do would be, well, I say the last thing to do. We should have actually done this first, which was to come up with some strings that the NFA accepts and see whether the DFA also accepts them. So if we start here at 1, one possible string would be just A. Why don't you put in the chat some other strings that are accepted? Remember, it's okay to pass through an accepting state. Your goal is just to end up on one of them. So you could do like AA, you pass through number 2, but you end up on number 4. Now the thing about doing AA is that we could also do it this way. That also ends up on an accepting state. So there's actually 2 ways on AA to end up at an accepting. Can we merge state 2 and state 2, 4 together? in our DFA, I mean, like, can we somehow combine these two together? No. These are actually two distinct states. One of them is labeled 2 and one's labeled 2,4. So in the DFA or in the NFA, in some cases you end up only in 2, and in some cases you end up in both 2 and 4. So these are actually two distinct states. Now, it could be that you can look at the DFA and go, you know, we could actually simplify this a little bit. We actually don't need one of those states, and we'll accept the same strings. And that might be the case, but then that would suggest that perhaps in the NFA, there was a way to simplify that. And that's not our goal here. Our goal is just simply to, given an NFA, transform it into an equivalent DFA, and don't worry about extra states or optimizing anything at this point. Yeah, so minimizing the DFA is another step that you can do. And I want to set that aside and say, if you take a course in programming language theory where you dive deeper into NFAs and DFAs, you'll probably learn about how to minimize the DFA, how to eliminate extra states that you don't need. But that's not our goal for this introductory course. So what are some other strings that the NFA accepts? So certainly not AB, that takes us to 3. But what about ABB? ABB. Is that one acceptable? So if you look at the NFA, we could do A, B, B, and then we don't end up in an accepting state. But if we do A, B, B, we do end up in an accepting state. So it depends upon which path you take. For an NFA, if there's multiple paths you can take and at least one of them ends up on an accepting, then the string is acceptable. So if I do it this way and I don't end up on accepting, but if I do it this way and I do end up on an accepting, that makes it acceptable. So this is actually, ABB will work. What about BBB? So if we do BBB, we can see that we don't end up on an accepting state. And if we do BB and then get stuck, we also don't end up on an accepting state. But if we do BBB, we do end up. So that one works. So does just 2 B's, and as well as 4 B's, or even 6 B's, or 7 B's. You just got to do the correct number of loops over here before you take one final leap over to number 4. What about like a whole bunch of A's? So that'll also work, right? You just got to loop over here the correct number of times before you finally come down to number 4. Or you could just say, I'm just going to loop here and just stay here. So that'll work. How about a whole bunch of A's followed by a whole bunch of B's? So you come over here, you loop, and then you come over here, and as long as you've got at least 2 B's, you can make your way over to number 4. If you only have 1 B, however, you won't make it. Okay, so we got a whole bunch of strings that are acceptable by the NFA. Let's try them out with the DFA. Let's try A. So we go here, and it works. AA takes you over here. ABB, ABB, good. 3 B's, 1, 2, 3. A whole bunch of B's. A whole bunch of A's. And then a whole bunch of A's followed by a whole bunch of B's. It actually goes like this. Loop around to this tight, come over here, loop around this one. So you can see with the DFA, there's no place where there's an ambiguous choice. You're always going to follow exactly one path, unlike in the NFA where there could be two or more paths that you could follow. All right. So that's basically how to transform an NFA into a DFA. But that's not how the computer would do it. The computer wouldn't have this diagram in its memory. It would have some kind of data structure. So let's see how to take an NFA and turn it into a matrix, a table, and then use that table to turn the NFA into a DFA. So here's an NFA over here. And we know it's an NFA because there's at least one place where there is an ambiguous transition, like right here. And I think there's another one. Oh yeah, here. So in our table, we're going to have the states listed down the side and the symbols across the top. And we're going to mark our starting state and accepting state. And then inside the table, just fill in the transitions. So if we're in state number 1 and we see an A, if we're here and we see an A, we don't go anywhere, so we'll leave that blank. If we're in state number 1 and we see a B, then that goes to 2 and 3. And then for state number 1 on a C, that doesn't go anywhere, so we'll leave that one blank. What we're trying to do with this table is capture all of the information that's in our NFA. Hang on a sec here. Yeah. Sorry, I was just checking something on my computer. Okay, let's do this again for state number 2. So if we're on state number 2 and we see an A, so if we're here, there's an A leading back to 1. And then if we're on 2 and we follow a B transition, I don't see any, so I'll put a blank. And then finally 2 on a C takes us to 3. And then if we're on a 3 and we see an A, nothing. 3B takes us to 2. And 3C takes us to 3 and 1. So if I haven't made any mistakes, that should capture all of the information that's in the NFA, that somebody who saw this table could take it and recreate the NFA from the information I've given here. It marks the start, it marks the acceptings, has all the symbols, and then all the transitions are in here. So let's pretend for a moment that we can't see this NFA. All we can see is the table. Let's try to turn that into another table that is just a DFA. So if you remember, as we were turning this NFA into a DFA, what we did was we started in the starting state, and then we checked to see what transitions are available to us and where those leaded. So we're going to do kind of the same thing, but we're going to use the table. We're going to start at the starting state and then see what transitions are available to us. And we'll add states down the left-hand side as we discover them, the same way we added states to the DFA drawing as we discovered them. So we're going to start at number 1. Let's put in our symbols across the top. And then looking at the table, we say if we were in 1 and we followed an A, we would go nowhere. So I'll put a blank there. If we were in 1 and we followed a B, we'd end up in 2 and 3. So I'll put 2, 3 there. And then for C, that's a blank, so I'll leave that a blank. So I've just discovered that 2, 3 is a new state, and I'll add that to my list. Okay, so now we're in this row. We're in the 2, 3 row. So take a look at the 2 and the 3 row here, and then we'll go through each one of the transitions. So here's the A transition from 2 and 3. I see that there's a 1 and a blank. So I'll combine those, and that becomes just 1. Do the same thing for the next transition. Here's 2 and 3, and we're following B. So I see a 2 and a blank. I'll combine those to make 2. And then 2 and 3 on a C. I see 3, 3, 1. Combine those to make 3 and 1, or 1 and 3. We just added 3 new states to the table. So I'll add those, and then we work down to the next row. So we're on this row right here. Okay, so we're in the 1 row here. We can basically just copy what we see here, because 1 on an A is going to go nowhere, 1 on a B is going to go to 2, 3, and 1 on a C is going to go nowhere. So we'll just copy that. Dash 2, 3, dash. Now, we didn't add anything new to the table, so we'll move on to the next row. This is the 2 row here. We can just copy this row. 1, dash 3. And we actually just added something new. 1 was already there, but we just added 3. So that becomes a new state to add. Okay, 1, 3. We're looking at this row and this row. On an A, we see nothing and nothing, so that's a dash. All right, 1 and 3 on a B. I see a 2, 3 and a 2. Let's put those together and make 2, 3. And then 1 and 3 on a C. I see a dash and a 3, 1. We'll put those together and make 1, 3. Didn't add anything new, so we'll go to the last row. The 3 row, actually we can just copy this. Dash 2, 1, 3. And we didn't add anything new, so we are now done. At least as far as filling in the table, the last thing to do is to mark our starting and accepting states. We've got our starting labeled already. The accepting is anything with a 3 in it. So that'll be this one, and this one, and this one. And then finally from this, we can draw our DFA. It's going to have 6 states. Here's the first one, and we can see that it goes to 2, 3 on a B. 2, 3 goes to 3 places. It goes back to 1 on an A. That's this one here. it goes to 2 on a B. And it goes to 1, 3 on an A. I guess I'll draw it over here. I hope this will work. I always like to draw my state diagrams so that the transitions don't cross each other if possible. But I don't necessarily know how this is going to turn out in the end, so we'll hope for the best. Okay, actually, you know what? I had state number 1 here. Now I didn't need to do this. I didn't need to do this at all because I already had it right here. So I really didn't need this one. So that means our diagram's only going to have 5 states in it, not 6. Okay, let's do 2 here. So 2 on an A goes back to 1. Uh-oh, I can see right now it's gonna cross. Oh, actually, I'll go this way. Yeah, I'll go around like this. And then this goes to a new one over here. You know what I'm going to do? I can see I might be able to rescue myself if I... this was labeled C. What I'm doing is I'm just moving this one. And then there. You know, sometimes it helps if you kind of make a rough draft of your state machine and then go back and clean it up later. All right, so I think I'm done with this row here. Let's see, I have 2 on an A going back to 1, good, and 2 on a C going to 3. Excellent. So now I'll turn my attention to the 1, 3 state. On a B, it goes back to 2, 3. And on a C, it goes to itself. So that was right here. And then finally, the 3 state on a B goes to 2. And on a C, it goes up to 1, 3. Oh, that worked out beautifully. Nice diagram with no overlapping lines. Sometimes you can't get around it. Sometimes there will be an overlap, but it looks nicer if they don't overlap. Okay, so this is an accepting, this one is, and this one is. Okay, so let's do a couple more of those. Now for this one, I'm not going to show you the NFA to start with. Let's just go straight from the table to the DFA table, and then from there to the DFA diagram. Put down our symbols across the top. And then we'll start laying out the states as we go down the side. So we'll start at 1, and then we'll just copy that row over. And we just added 3. We already had 1, so we don't have to put it down on the table again. But we just added 3. And we can copy that row, 3, 1, 2, and nothing. We just added 1, 2. So now to do that one, look on both these rows, not those, look on these rows, and on an X, we can see it goes to 3. 1 and 2 on a Y goes to 1 and 2. And 1 and 2 on a Z goes to 1 and 3. And then we just added 1 and 3 as a new state. So you fill in that row. Put it in the chat. What would the contents of that row be? 1 on 3 on an X goes where? 1 on 3 on a Y goes where? And 1 on 3 on a Z goes where? All right, so good. X goes to 3. So if I look at these two rows on an X, I see a 3 and a 3, and I combine those, and that makes 3. Good. How about Y? Y goes to 1 and 2. So if we look at these two rows and a Y, we got 1 and 2 there, combine them together. And then on a Z, 1 and 3 on a Z, nowhere. Oops, I don't know why I wrote 1 and 3 there. Should be nowhere. And then our accepting is anything with a 3 in it. So our DFA is going to have 4 states. Starts at 1. On an X, it goes to 3. And on a Y, it goes back to itself. 3 on an X goes to itself. 3 on a Y goes to 1, 2. 1, 2 on an X goes back to 3. 1, 2 on a Y goes to itself. And 1, 2 on a Z goes to 1, 3. And then finally, 1, 3 on an X goes back to 3. And on a Y goes back up to 1, 2. And then this is an accepting, and this one is. Okay, so let's do the second one. So here's our table. We got our symbols, our start. We'll copy this and this. And then we just added 2 and 3 to the table. So what comes next? What will be the 2 entries for this next row? Okay, for A, it'll be 1, 3. And for B, it'll be 1, 2. Actually, let me see here. I'm just looking at what the answers here are. So for B, if we're on 2 and 3, and we're doing a B, we're going to combine all these together. And I see 1, 2, 3. And then we just added 2 new states to this. Okay, so next, what are the 2 entries for the 1 and 2 row? So what goes under A and what goes under B? Let's see, under A, if we're looking at the 1 and 2 row, we're going to combine these together, and we get 1, 2, 3. And then for B, combine these together, and we get 1, 2, 3. And then for the last row, we didn't add anything new, so we got 2 more entries to fill in. What does 1, 2, 3 on an A do and 1, 2, 3 on a B do? So you're going to look at all 3 rows. You're going to combine all these. So that obviously makes 1, 2, 3. What about for B? This one. So look at all 3 rows. That also makes 1, 2, 3. And then anything with a 2 or a 3 in it is going to be accepting. All right, so state number 1 on an A goes to 2, 3, and on a B goes back to itself. State 2, 3 on an A goes to 1, 3, and on a B goes to 1, 2, 3. I feel like I did something wrong here. What happened? I see this here and I see this here, and somewhere I think I made a mistake. So what happened here? Let's just go back and double check here. So 2, 3 on an A, so this one and this one on an A goes to 1 and 3. That's good. And then 2, 3 on a B goes to 1, 2, 3. So that's good. I should have written 1, 3 here, and I wrote 1, 2. I hope that doesn't change things too much. So I goofed. So 1, 3 on an A, whoops, goes to 2, 3. And 1 and 3 on a B goes to 1, 3. Was anybody else like confused when I was doing this? I'm going, it looks like I didn't do something right here. So now let's go back and rescue this. I'm just going to start over again. So 1 on an A goes to 2, 3, and on a B goes to itself. And then 2, 3 on an A goes to 1, 3, and on a B goes to 1, 2, 3. Okay, 1, 3 on an A goes back to 2, 3, and on a B goes to itself. And then 1, 2, 3 on an A goes to itself, and on a B also goes to itself. And then here's an accepting, here's an accepting, and here's an accepting. Okay, I think that looks better. So you can see you can do this transformation from an NFA to a DFA using just a table. You don't need the original diagram. So in fact, the computer just does this to this, and essentially it stops there, right? Of course, the computer doesn't draw the diagram. And then from this, you've essentially now got a table that you could use to build your chain of if-elses, or you could you can actually implement this data structure probably as something like a dictionary in Python or a hash map in Java, and then use that to run your regular expression execution engine, which, if you recall, was just this loop that loops over the string that you're inputting, and then either has a chain of if-elses or uses this dictionary lookup to figure out what state to go to next. And it just churns through the symbols in the string, and then if it ends up in an accepting, it's done. So let's move on, and I'm going to show you a new concept. And these are NFAs with epsilon transitions. You can see right here, I've got this transition that's labeled with an epsilon, which means that following that transition doesn't consume any characters in your input string. So if you're going through this state machine, you can start at state number 1, you consume an A, and then you could either jump ahead to the accepting state, or you could consume a B. And so when you have these epsilon transitions, that makes it an NFA also, because you don't know whether to jump ahead or consume the symbol without looking at the next symbol. This state machine accepts 2 strings. It accepts A, B, and it accepts just A. How about the second one? What are some strings that it accepts? One of them is XY, which you can get by going straight through. But what are some others? So we could do just Y, right, by skipping the X and then going straight through to the Y. What's another string that it accepts? So another one could be X, Y, and then jump back and do another Y. In fact, we could repeat that process over and over again. And then another string we could do would be to skip this X and then just go on and do a bunch of Ys. So it kind of looks like it's a regular expression, or the strings it accepts are optionally an X followed by as many Ys as you need, as long as there's at least one. So maybe a equivalent regular expression for the first one would be A or AB. That's one way to do it. We could also do A and then followed by B or nothing. And then for the bottom one, it would be X or nothing, followed by at least one Y, and then any number of Ys after that. Yeah, so epsilons are kind of like little shortcuts. You can either follow them and then skip a symbol, or you could not follow them and go ahead and consume that symbol. But it's an NFA because you don't know whether to skip ahead or consume the symbol unless you could kind of look ahead at some of the subsequent symbols. So let's take a look at this one. Here I've got an epsilon right here, and I also have a couple of places where there are ambiguous transitions. So this is definitely an NFA. Let's see if we can convert it to a DFA using the same techniques that I've shown you. We're not going to deal with the table just yet, but just kind of like exploring the map. Let's see if we can convert it into a DFA. So we're going to start in state number 1, and we see that there's an A and an A. That means there's only one A coming out, but it goes to 2 and 3. So if we follow A, we go to 2 states, 2 and 3. Now we're in 2 and 3 at the same time. What do we see? There's a B coming out, a B coming out, and a B coming out. So there's only one B coming out, but where does it go? So if we're in 2, it would take us to 4. And if we were in 3, it would take us to 4 and 2. So apparently following a B transition out of 2 and 3 takes us to 2 and 4. And then from 2 and 3, there are no A's going out. So we're done with that state. Okay, 2 and 4. We're now in 2 and 4 at the same time. Oh, actually, let me back up again. Let's go back to 2 and 3. Let's go back there for just a moment. So we're in 2 and 3. Remember we followed the B? So this B here took us back to 2. This B here took us to 4. And because of the epsilon, it also took us back to 2. I guess you could say the epsilon's kind of like, you know, from science fiction, like a wormhole, right? You know, you sit here and then you enter the wormhole and you find yourself zip back over here as well. So if we were in 2 and we followed the B, we'd end up in 4, but the epsilon would zip us back to 2. So we'd end up back in 2 and 4. Likewise from the 3. If we follow the B, we end up in the 4, and then the epsilon here takes us also back to 2. So this is still correct. We still end up in 2 and 4, but our diagram, or the way we got there, is a little more complicated than I initially described. Okay, so let's go back to 2 and 4. So we're in 2 and 4, and I see an A, and I see a B. Okay, so I know there's an A and a B. If I was in 2 and 4 and I follow the A, I end up only in 3. And if I was in 2 and 4 and I follow the B, I go over to 4, but the epsilon takes me back to 2. So that means this one loops back to itself. So I'm not saying that once you follow the B here, you end up at 4, and then you automatically go back to 2. What I'm saying is, if you follow the B transition out of 2, you could end up in 4 and stay there, or you could take the epsilon and also go to 2. So you end up in both states simultaneously. Remember, the epsilon is kind of optional. You can either do the epsilon transition or not. So you either stay in the state or you zip ahead to the next one. Number 3, if I follow a B, there's no A's coming out of here. So if I follow a B, I go to 2. And if I follow this B, I go to 4, which also takes me back to 2. Okay, so if I was in 3, I'd go to 2, and it'd also go to 4, and then to 2. So that means that 3 on a B goes back to the 2, 4 state. And there's no A. All right, if I haven't made any errors, I think that's our diagram. We just have to put in an accepting around the 2, 3 and an accepting around the 3. Let's just make sure. What are some accepted strings for the NFA? So one would be just A. So even though there's an A that takes us to a non-accepting state, there is one that takes us to an accepting. So this one is okay. Also, what else could we do? We could do A, B, A. And we could do A, B, A, what else? B, A. Let's see, we could do A, B, B, A. We could also do A, B, and then any number of those B's. We just have to get ourselves out of this loop. So we can do one final A when we're done. And then some strings that are not accepted would be A, B, and that would be it. So A, B does not work. So no matter if we did it this way, or if we did it this way, or this way, A, B does not take us to an accepting. What's another string that can't be accepted? Obviously, just B alone won't work, right? But that's just an error. There's just like no way. What I'm looking for is there a string that ends up on either 2 or 4 and is unable to go to 3? So while you're thinking about that, let's just make sure that all of these strings here are acceptable in our DFA. So we've got just A, good. A, B, A works. A, B, A, B, A. A, B, B, A, and then A, B, and a whole bunch of B's, and then a final A. And then finally, A, B does not work. Boom, right there. I can see also in this DFA that A and then a whole bunch of B's would also not work. And let's see if those don't work in the NFA. So we've got A, and then we got a whole bunch of B's, and it takes us to here. Or we could do it this way, or we could do it this way, right? All of those don't get us to number 3. Okay, so that's how you deal with the epsilon transitions. If you wind up on a state that has an epsilon coming out of it, you can either stay in that state or you can follow the epsilon and go to wherever it's going. So let me introduce you to something called Thompson's constructions. So these are a way to take any basic regular expression that uses the alternation, the star, or the grouping, and turn it into an NFA. Now, I'll go on record and say that these constructions are very slightly different from ones you're probably going to see on the internet. You know, you watch a YouTube video, not by me, by someone else. The one down here on the bottom, this one is the same, but these over here are a little bit different. That's because the ones you'll see on the internet actually have like additional epsilons coming in and out. And you know, that's fine, and it's probably more correct to do it that way, but it adds a whole bunch of epsilons to the diagram. And I think for these purposes, again, in an introductory course, what I've shown you here is good enough. You can take pretty much I can take any basic regular expression and turn it into an NFA using these constructions if you do, you know, a little bit of manipulation of the diagram. But the goal here really is to just be as simple-minded about it as you can. Anytime you see a sequencing, you just draw states in a line. Anytime you see a branch using the OR, you just draw a branch that goes back to another state, one additional state. And then anytime you see the star, you turn it into this complicated, I call it either the boat or the UFO diagram because it looks like, you know, one or the other. And the whole reason for having this complicated one for the star, instead of just simply a loop like we did before, is to ensure that, you know, kind of like once your state machine goes down a branch, it gets stuck there and it can't come back and make a different decision. If this was our regular expression, A, B, or C, C star, and we did the C star here as a star, or not, I mean as a loop, then the problem here is that we could do a whole bunch of C's and then go do an AB. But that's not allowed by our regular expression. Our regular expression says you're either going to do AB or you're going to do any number of C's, one or the other. And so so one way we've managed that is by having like this little branch and then a loop off of that. But it requires like a little bit of thought and optimization to be able to pull that off. What I'm suggesting here with this construction is that all you have to do is anytime you see the star, you just drop this in. And you don't worry about like, do I have a situation where I create a branch that could be followed later on. By using this construction over here, it'll guarantee that once it enters this portion of the state machine, it will either do this section or it'll do this section and skip over it. It won't be able to like come back and go down another branch. So that's the purpose of this complicated looking construction for the star. Oops. So let me quickly show you a couple of examples of how to use the Thompson's constructions. And then next time, so that'll be next, Monday, I will show you how to use those constructions in order to do a complete transformation from a regular expression into an NFA and then a DFA and then finally a DFA diagram. Okay, so let's come up with a regular expression that we want to convert. Let's do something like, I don't know, A, B, let's do A, B, or A. Let's do C. Followed by D star, okay? So there's our regular expression we want to do. We're actually, using all three constructions here. We got sequencing, we've got alternation, and we've got the loop. So when you look at this regular expression, the first thing you do is kind of like go like, what do I see here? I mean, obviously I see alternation, I see looping here, but what is like the primary thing that's happening? What's the big picture? The big picture here is that I'm sequencing three smaller regular expressions. I've got the A, I've got the B or C, and I've got the D star. So I'm going to make a sequence out of those three pieces. So here's my A piece. And I'm not even going to break down the B or C just yet. I'm just going to write it as B or C because I've got a sequence of that. And then here's my D star. Okay, so I haven't worried about breaking apart individual pieces. I'm going to do that next. But I'm just going to look and see I got a sequence of three things. I'm just going to write them out. A, and then B or C, and then the D star. Now we're going to start breaking apart the individual pieces. So the A doesn't change, but the BC becomes this. And you can see that all I did was, if I have two things that are alternating, I just turn them into this. So you really shouldn't put a whole lot of thought into this. You just simply look at what the operation is in the regular expression and then just turn that into the equivalent state machine piece. Okay, and now we've got the D star, so that's going to turn into that UFO. So this piece right here, these two states went over here, and then this D star here is filling in this whole section over here. So you look over here, and here's how you do it. You got an epsilon here, you got an epsilon on both sides. You got one that skips over everything, and then one epsilon that skips over or just loops back in the middle. And then you finally got your one symbol sitting in the middle of this diagram. So you got an epsilon here, an epsilon here. There's the D epsilon that goes back, and one that goes all the way through. And that's how you do it. So we could do A, B, and then any number of D's. We can do A, C, and then skip the D's because one option is that we don't do any. We can do A, B, and just one D. We can do A, C, and one D. We can do A, C, and any number of D's. Okay, let's do one more. Let's do, I think I'll do, how about X, and then X or Y star, followed by Z or X. Okay, again, I see three things sequenced up. So here's the X. And then I have X or Y star. Again, don't worry about breaking it up just yet. And then finally, Z or X. and then start replacing each one of those sub pieces with their equivalent Thompson's construction. So this one here in the middle, this is the star construction. So it's going to expand out to be these 4 states. We've got an epsilon here, an epsilon here, one that goes back, one that goes forward, and then in the middle, I've got X or Y. So what I did was I just took the star and I basically converted it into the star construction, which is this here, and right in the middle, I just put whatever the star was modifying. And the last piece is the Z or X. Again, just a branch going back to the one following state. And the last piece is now to break up this Y or X. That's the last step. And of course, that's pretty easy to do. And there we go. So you end up with a NFA that potentially has lots of epsilons. But we can deal with those. We can turn that into a DFA. There's just going to be lots of places where we could skip over some states, but we can handle that. We can do this, and we'll do that next time. But really, at this point, you have all the pieces you need to be able to turn any regular expression into an NFA, and then from there into a DFA, and then from there into a program. But we'll show you some examples next time. So what I'm going to do now is take a short break, probably about 10 minutes or so, and then when we come back, we'll learn about programmers' regular expressions. So programmers want to use regular expressions, but they want to get work done. You want to be productive. And if all you have is the alternation and the star and the grouping, you can construct any regular expression, but there will be some convenient shortcuts that I'll show you that'll make it a little bit easier to construct the kind of pattern matching that you want to do in computer programs. So we'll come back from a break and we will go over that.
Recording stopped.
All right. So let's see, I didn't hear from you folks over the past 10 or 15 minutes, probably because I wasn't really asking you any questions. But you kind of get the idea of the epsilon now, that it's kind of like a continue in a for loop, but it's a conditional continue, right? You can either elect to do it or not, depending upon what's coming next. So are there any questions while we are on our little break? I didn't have any Zoom folks today. I've only been talking to the YouTube people. I don't know what happened to my Zoom folks. Usually I have 2 or 3 of them, but today I got no one. That's why I had to pause in the middle. It's like, am I on the right Zoom? Am I on the correct Zoom meeting? And I am. I looked at my Zoom ID. And I go, yeah, that's the right one. So I don't know where everyone is today. Maybe it's because it's such a beautiful day. They're out at the park or something. Well, let me turn on some music. And so maybe while we're waiting, I'll play a video game. This is a classic 8-bit computer game called Load Runner. Oh, better get going. Turn off the music, shouldn't I? Hang on, I gotta beat this level first before I do that. Can't take my eyes off it. Uh-oh. Oh, there we go. Oops, better go this way. Music off. There we go. Not much in the way of sound effects, except when you're picking things up. So the goal of this game is pick up all the little gold boxes, and of course avoid the bad guys. And you can drill holes in the bricks. Ah. This was one of my favorite games when I was a kid. I played this for hours. Uh-oh, I am trapped. I'm not going to do that next time. Go the other way. Go get that one, and then come up. pick up that one. Almost done. I guess I'll get this one. Uh-oh. Oh, no. I don't know why I did that. Seemed like a good idea at the time. Okay, to get this one, I gotta drill 2 holes, then 1, and then drill out that one. And that'll do it. All right, this one should be fairly straightforward to do. Over here, here. Oh, there we go. I just gotta make my way over there. Last one. I'll come back and get that one later. Oops. Let's go this way, up. Grab this one. Come on. There we go. And oh, I gotta go get that one on the top. Okay, that one's gonna be a little trickier. These guys don't want me to get that. Come on. Up, 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 up. Here we go. Oh, I can get it. There we go. And there's one more to get. I just gotta get it out of this guy's hands. Let's see. Come down here. Okay. All right, that's it. Enough playing games.
Recording in progress.
Okay, here is one of our last assignments. This is the last computer assignment, and then we're going to have one more assignment. This is going to be a pen and paper assignment. And then that'll be it for the content of the course for the semester. So let me walk you through this assignment here really quick. This is lab number 8, regular expressions. So there are 5 files to download. You can either download them individually, got right here, or you can download a zip file, unpack that zip file on your computer, and then upload the 5 files separately to Jupyter. Unfortunately, Jupyter doesn't have a way to unpack zip files itself. So you got to download either the 5 files separately or download the zip file, unpack it on your computer, and then upload it to Jupyter. So all the instructions are in the Python notebook file. So once you've uploaded the files, we can get started. So let's take a look at these 4 files first. The one called contacts is just simply a text file containing names, addresses, phone numbers, email addresses of a whole bunch of fictitious people. For those of you not in the United States, this is typically what our addresses here look like. You've got someone's name, you've got their street address, possibly with an apartment number, and then the city, the state, and then what's called a zip code, which is kind of like a postal code. So they all kind of follow the same format: name, address, city, comma, state, and then a zip code. And we've also got phone numbers, and we've got email addresses here. So that's the contacts file. And then this one here, this one called program. This is a fictitious programming language. It doesn't correspond to anyone really in reality. And in this one, the keywords like class and var and function and return, those are all capitalized, and everything else, all the identifiers, are lowercase. I'm just making it a little bit easier for you to do the pattern matching on this particular program. So the keywords are in uppercase, the identifiers are in lowercase, and then you've got numbers and operators as usual. And then this one called Perl. Now this is an actual programming language. This is a language called Perl. And you know, if you kind of take a step back and blur your eyes a little bit, it looks a little bit like C or Java. You've got things like whiles and, well, I don't have any other examples of things like ifs and loops, but they all look basically the same as they do in Java and C. But variables here in Perl are preceded by either a $sign or an @ sign, and that actually tells you what the type is. $sign means that this is what's called a scalar variable that holds either a string or a number, and then the @ sign tells you that this is an array variable. So arrays start with an @ sign. So here's a variable, here's one. These are all variables here. And in fact, this is a variable too, this @ and underscore. That's also a variable. And then finally, these lines that begin with the hashtag, or what we call the pound symbol sometimes, is a comment. Comments start at that symbol and go all the way through to the end of the line. So everything after the hashtag symbol is just completely ignored by the program. So there's a comment, there's a comment, there's one, here's one, here's one, and even this first line is also a comment. And then finally, weblog is a few lines out of a file that is generated by a web server. Web server generate log files that contain information that a web administrator would find interesting. Things like the IP address of the web browser that is connecting, the date and time of when the connection or the request was made, and then what file was requested, and also any error codes on the end. Some of these lines are so long they actually just wrap around to the next line. So this line number 2 here is actually one continuous line, not two separate lines as it appears on the screen. But we still have the IP address, date and time, the file that was requested, and any error codes. The very last number is the size of the file. 13 lines in this file altogether. So we're going to be writing regular expressions to match things out of these files and pull them out. So let me talk to you a little bit about programmers' regular expressions. Regular expressions in practice are used in programming languages like Python, Perl, PHP, Java, Sed, Awk, grep, and others. And in programmers' regular expressions, any character that isn't one of these special characters is taken literally. So if you have a string like A, B, C, that means you want to match the string A, B, C, an A followed by a B followed by a C. You concatenate letters together by just writing them in sequence. There's no reason to put any other symbols between them, just A followed by B followed by C. But the meta characters here, meta characters are characters that have special meaning, are the ones that you're probably familiar with. There's star, there's alternation with the vertical bar, and there's grouping. But there's a couple of other ones that are useful. There's dot, matches any one character. So basically any character you can type on the keyboard is matched by the dot. So any one character is matched by that. And then finally the brackets here are used to match one character out of a set of characters. For example, bracket A, B, C, D will match any one character out of the letters A, B, C, or D. It's kind of equivalent to doing, actually it is equivalent to doing a group with A or B or C or D in it. It's just a shortcut for that. These two are equivalent to each other. Matching any one character is basically A or B or C, or Z, or capital A or capital B or capital C all the way up to the big Z, or exclamation mark or at, or like I said, basically anything you can type on the keyboard is represented by that dot. So here's some examples. Let's say we want to match whole numbers. Numbers like 1, 2, 3, and maybe just 6. And 7, 8, 9, 0. Right? So basically any non-negative number. So with regular expressions, you have to step back and not think about these things as numbers, but think about them as sequences of characters. What does a number look like if you're just looking at it character by character? So I see here a digit. Here's a digit. Here's a digit. These are all digits, right? These aren't just numbers. They're just sequences of digits. And a whole number always has at least one. So we could write a regular expression to match that. We could do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, followed by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then any number of those. So there has to be one digit followed by any number of subsequent digits. But that's a lot of typing. So there's one shortcut that you can use, and that's to put a dash in between a starting character and an ending character. If you want to accept any one character out of a range of characters, you do it like this. So one of these, any character in the range is 0 through 9, followed by any number of subsequent characters, 0 through 9. And also, if you wanted to disallow 0, if you say that's not a whole number, technically that's not a whole number, then you would change that. You'd say 1 to 9 as your first character, and then 0 to 9 on subsequent ones. And then that would disallow 0 by itself. How about matching words? What does a word look like? You know, obviously, word is a word. And, you know, that's a word. Basically, now, what pattern matching, what regular expressions can't do is validate whether that's an actual word. So something like X, Y, Z will still get matched, right? Because it seems to look kind of like a word. And what if you also want to include uppercase letters? What if you want to do match as one of your words? So there's a capital letter there. And what if we also wanted to do A, B, C, all capitals? So we can combine the ranges of characters using the dash, but in this case we're going to do little a to little z, and then big A to big Z. No spaces in there. If you put a space inside the brackets, it'll actually match a space. Same thing for spaces anywhere else. Space doesn't have any special meaning. If you put a space in your regular expression, it will attempt to match a space in your pattern. So try to omit spaces unless you really actually want them. So here's something that'll match something that looks like a word. Any letter followed by any number of additional letters. Now, you might be thinking, why can't I do like little a to big Z? Why won't that work? Well, it won't work because it's really just writing a loop that looks to all the characters starting at the beginning character and going to the ending character. And that might include some characters that you don't want. So here is the little character, little a, and here is the big Z. And you can see that the ASCII value of the big Z is 132, and for the little a, it's 141. And so when it attempts to write a loop that goes from 141 to 132, it won't work because the loop doesn't go backwards. So if you do little a to big Z, you'll actually get a group of characters that includes nothing. And if you try to write it the other way, big A to little z, then if you start at big A and go to little z here, sure, that'll include all the capital letters and all the lowercase letters, but it will also include these and these up here. And those are probably not what you wanted. So those include the uppercase letters and lowercase letters and some extras. So these will not work. If you want to match lowercase and uppercase letters, this is the way to do it. How about zip codes? So here in the United States, these are called postal, in other parts of the world are called postal codes. Here in the United States, they're basically, they take two forms. They can either just be 5 digits, or they can be 5 digits followed by a dash followed by 4 digits. So they're called 9-digit zip codes. So they look like these. Here's a 5-digit zip code. Here's another one, and here's a 9-digit zip code. All right, so to match the 5-digit zip codes, it's 0 to 9, 0 to 9, 0 to 9. It's a lot of writing. And I'll show you some shortcuts for this as well in just a couple minutes. So there's our 5-digit zip codes. And then our 9-digit zip codes. There's 5 digits, and then our dash, and then 4 digits. All right, so 5 digits, and then 5 digits, a dash, and then 4 digits. So if you want to accept either one of them, either a 5-digit zip code or a 9-digit zip code, you got to do it like this. That's a lot of writing. You know what I'm going to do? I'm going to do some copy and paste here. This. Right there. And then a big old or. And then this one. Hope I got it all in. I didn't quite get it all in, but there it is. That's the idea. Let me just move this over. I don't know if I can do this. Can I get it all on the screen? No, it's the best I can do. So it's important when you're matching these zip codes to put the longer one first, followed by the shorter one. If you put the shorter one first, then if presented with a longer zip code, it'll just pick out the first 5 digits and go, okay, got it. By putting the longer one first, it forces it to try the longer match first. And then if that fails, then it tries the shorter one. Okay, so that's the general idea behind basic regular expressions. These ones that I showed you here are BRE, basic regular expressions. But programmers said, I want even more. We want more. So there are extended regular expressions, which add a few more symbols. And there's actually even more symbols that added, but these are the useful ones for us. So there's plus, which means 1 or more. You're already familiar with star, that means 0 or more, but plus means 1 or more. Now, really, you can turn plus into 0 or more. So x, I won't use x, let's use like a plus is equivalent to a star. So plus just means 1 or more, but you can break it down into a basic regular expression just by repeating that symbol. So an a followed by 0 or more a's is the same as 1 or more a's. Question mark means 0 or more, or optional. So a question mark is the same thing as a or epsilon. It's either there or it's not. There's a repetition operator. You just put a number inside of curly braces. So like a and then a curly brace 3 is the same thing as just a. And you can also use a minimum and maximum. So repeat as few as m times and as many as n times. So like a curly brace 2, 4 is the same thing as AA, or AAA, or AAA. So each one of these extended regular expression metacharacters can be converted into an equivalent basic regular expression. Nevertheless, using these extended regular expressions gives us much easier ways to represent things like numbers and words and zip codes. So these here are basic regular expressions. I already showed those to you. The equivalent extended regular expression would be 0-9 plus for numbers, and little a to little z, big A to big Z, plus for the words. And then the zip codes become really easy. 0-9 repeated 5 times. If you want to do the whole thing, where it's either the 9-digit zip code or the 5-digit zip code, it looks like this. So there's our 9-digit zip code or the 5-digit zip code. And another way to think about it is there's always going to be that 5-digit portion. The 4-digit suffix is optional. It could be there or not there. That means there's another way to write this. You could do 0-9 repeated 5 times, followed optionally by a dash, and 0-9 repeated 4 times, grouped together with a question mark. So it's always going to be a 5-digit zip code, followed optionally by a dash and a 4-digit zip code. And you want to group them together so that the dash and the 4 digits go together as a unit. So they're either both there or they're both not there. What you wouldn't do is, or what would be incorrect, I should say, would be, let's put the 5 there, and then dash, question mark, and then 0-9, 4, and question mark. And that'll mean you got your 5-digit zip code, but then you've got a dash that's optional, and then a 4-digit zip code that's optional, which means you could do something like 1, 2, 3, 4, 5, 6, 7, 8, 9 without the dash, and that would be acceptable because you made the dash optional. So this will not work. These others here, those will work fine. Okay, so let's take a look at some of the problems in the assignment. Here's a table of those same metacharacters I just talked about. You've got star, plus, question mark, one out of a range of characters, any one character, or, grouping, repetition. And then if you do want your patterns to actually match one of these metacharacters, then you put a backslash in front of it. So backslash dot means to actually match an actual dot instead of any one character. If you actually want to match a $sign, you have to put a backslash in front of it because a $sign is a meta character. We're not going to use it in this assignment, but it is a meta character that matches the end of the string. And then finally, like I said, a backslash in front of any other meta character will let you match exactly that character. So here are some common regular expressions. We got any one digit, one or more digits, any one letter, uppercase or lowercase, 3 lowercase letters. Here's an optional minus sign followed by any number of digits. So this would be a way to do like what am I trying to say? Integer numbers. So it could be positive or negative. Dot star is a nice regular expression that matches any number of any character. So to do this assignment, before you start, you're going to upload those 4 files. And then this is the part of the Python program I've already written for you. There's nothing you need to do to this. All you have to do is just execute this cell, and it will define the function that you need for this assignment. So execute that one, and then move on to problem number 1. So problem number 1, find all the numbers in the text out of this contacts file. Remember, the contacts file looks like this. So we want to find all the numbers. Here's a number, here's a number, here's one, even though it's a zip code. Here's 3 numbers. Here's a number, here's a number, here's one. 3 more numbers. So anything that represents a number, no matter what it is. Replace the to do here with the a regular expression that will do what you want. So let's go ahead and do a number. That was going to be 0-9 and then a plus. I already suggested that was a way to do that up here, right? 1 or more digits. Okay, execute that cell, and it will show you a list of all the numbers it found. And you might want to visually check. Is 1116 one of the numbers? And it is, right there. Oops, I need to refresh my notebook here. Is 42 the next number? There it is. So that looks pretty good. Let's move on to the next one. Extract all the words in the text. So we already have a regular expression for doing words. It's either this one or this one. So you'll go ahead and put that one in there and then execute the cell and make sure it looks okay. Problem number 3, zip codes. Well, we already know how to do that. So here's problem number 3. Here's one, oh, not that one. Here's one we could use for zip codes. Put that one in, try it out. Problem number 4, email addresses. All right, so let's talk about email addresses. It says here, email addresses always consist of a username, followed by an @ sign, followed by what's called the host name. The username consists of 1 or more letters, numbers, dots, dashes, and underscores, and the host name consists of letters, numbers, dots, and dashes. So an example email address would be like bbrown@gmail.com. That's not my actual email address. That would be one. Or we could do sam@yahoo.co.uk. So the username portion goes in front of the @ sign, and the host name portion goes after the @ sign, and can consist of letters, numbers, dashes, and dots. So let's break this down into their individual pieces. So we've got the username portion, and we've got the host name or domain portion. So the username portion can consist of, looking at here, letters, numbers, dots, dashes, and underscores. There's actually more characters you can use here, but this is good enough for us. Letters, numbers, dots, dashes. Letters, numbers, and then since the dot is a meta character, we need to put a backslash in front of it. And since the dash is also a meta character used for the ranges of characters, we need to put a backslash in front of it. And then finally, underscore. Underscore is not a meta character, so it can just sit by itself. So one or more of those. Letters, numbers, dots, dashes, and underscores. One or more. And then we've got our @ sign, and that's not a meta character either. And then finally, the hostname portion, which consists of letters, numbers, dots, and dashes. There are no underscores allowed in host names. That's actually an internet rule. You cannot put underscores in a host name. So letters, numbers, dots, and dashes, and one of those, one or more of those. And for our purposes, that'll work. So what this, of course, this regular expression does not do is validate the email address, make sure it's a real one. It also would allow some things that aren't email addresses. It would allow something like dash, 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 at, dash, 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 right? But again, this is probably going to be good enough. If you are someone who needs to harvest email addresses, you need to go through messages you found on the internet and just pull out things that look like email addresses, you might use a pattern kind of like this. And again, you're going to do validating that it's an actual email address as a separate step. And you could, if you wanted, write a regular expression that is more comprehensive to get things that are actual, that follow all the rules for email addresses. And I'll tell you, they're complicated rules. Here is the actual regular expression for an email address. Let me bring it up on the screen here. I found this on Stack Overflow, and there it is. Okay, so you can see that actual real internet email addresses are much more complicated. By the way, there's the @ sign right there in the middle of the whole thing. And the nice thing about the Stack Overflow answer is it breaks it down character by character. The state machine that is used to implement and validate email addresses this way. And again, it's not validating that there's an actual recipient reading the email address, but it is at least going through and making sure it follows all the rules for an email address. Okay, so you're going to go ahead and put in the regular expression for an email address. Give that a shot. Number 5, problem number 5. This is using program.txt, which was this fake programming language. Extract all the numbers in the program. You know, keep in mind that they could be a decimal amount and they may be negative. So here are the numbers you should find: 1.8, 32, negative 2.547, 7, and 20.0. So let's go over that. Like, how would you match floating point numbers instead of just integers? So here are some examples of floating point numbers. You got 123.45 and negative 67.89 and negative 0.123 and just 3 and 0.14. So how would you match those? Well, we can see that we've got a negative sign that's either there or not. So we got a negative sign that's either there or not. Now the dash outside of the square brackets is not a meta character, so we don't need a backslash in front of it. It wouldn't hurt if you put one on there, but it's actually not needed. So we got an optional dash. And then we have the integer portion of the number, which may or may not be there. And then we have the decimal portion of the number, and the dot always goes with at least one digit on the end, right? So you would never have a number that's just like, 67 point. Actually, you could have that, but we'll disallow that for our purposes. Okay, so the integer portion would be like 0-9 star, because we could have 0 or more digits out in the front. And then we have the decimal portion. So we got a dot, and now here we do need a backslash because the dot is what we actually want to match. We don't want to match any character. We want actually a real dot. And then 0-9 plus. And that is optional. You don't have to have that there. So that'll be something you can plug in there. Number 6, extract all the identifiers. Identifiers are names given to things like variables, function names, and so forth. In this programming language, they're composed of lowercase letters only. So come up with a regular expression to match those. Problem number 7, we're going to use the Perl file, which looks like this. Extract all the variable names. So in Perl, variable names start with either a $sign or an @sign. The next character can be a letter or an underscore, and the rest of the variable name can be letters, digits, or underscores. So come up with a regular expression that will match those variable names. Problem number 8, comments. Comments begin with that hashtag symbol and go to the end of the line. Now, regular expressions already matched line by line, so you don't have to worry about how do I match the end of the line. That's already handled for you. What you need is a pattern that will start with the hashtag and then will match anything else that follows it. So anything that starts with a hashtag and goes from there on out will be matched by this regular expression. I'm not going to tell you what the answer to this is, but I've dropped enough hints, hopefully, in this walkthrough for you to be able to do that. Starts with a hashtag character and is followed by anything else. And then the last two problems are go through that web log, that web server log file, and pull out the IP addresses. IP addresses are 4 numbers separated by dots. And then finally, extract the dates and times, which looks like this. It's a 2-digit date slash a month slash the year, and then colon separating the hours, minutes, and seconds. And then last problem, extract the image file names, which end in .jpeg or .png. File names can contain letters, numbers, and underscores. So we want just the file name, not the whole path. For example, we want just header.jpg here, not this whole thing. So you've got a file name that ends with either .jpeg or .png. So that's your assignment. Let me scroll all the way back up to the top. So there's a bit of code at the top. You just need to execute this cell. You don't have to worry about anything else inside of it. And then you can start doing the problems. So as before, when you're all done, you're going to download this as a Python notebook, upload it to Canvas, and then I will take a look at it. So hopefully you'll enjoy doing this assignment. It's kind of like problem solving, right? You've got this problem you need to solve. You want to solve it in a way that is general enough that it grabs what you're looking for, but not so general it grabs too much, and not so specific that it grabs only that and wouldn't work on any other file. So imagine for for example, the contacts file here, imagine that you had, different kinds of email addresses in it. You have, or maybe the web log file here. Like think about, these are the IP addresses, but how can I make it general enough that it grabs just these, but not like, the numbers that are over in here. But not so specific that it won't grab other IP addresses that might appear somewhere else, right? So that's the kind of thing you have to think about. And I'll have to say that almost all of these files, except for the program file, but like this Perl program, that's an actual program I had to write at one point. This is a snippet of it. Basically, what it does is it takes someone's last name, first name, and student ID number, and it pulls out the first 4 letters of their last name and the last 4 digits of their student ID number and sticks them together. And then this is a way to like construct someone's password, a known password out of their name and student ID number. So sometimes that's where I find inspiration for assignments like this, just out of stuff that I actually did in real life. Okay, so that's your assignment. Hopefully you'll have fun with this. Again, it's kind of like solving little puzzles. And I enjoy writing regular expressions. I know there's a lot of people that hate it, but I actually enjoy writing regular expressions and trying to come up with a good regular expression that matches what I'm looking for, not too much, not too little, exactly what I'm looking for. And so hopefully you'll have some fun too. Well, I think that's the end of today. We've got a little extra time, but I'll just recap what we're going to do over the next couple of days. When we come back on Monday, we're going to put the Thompson's constructions together again and use those to convert regular expressions into NFAs. And then from there, we'll turn those NFAs into DFA tables and then into DFA diagrams. And then we'll do a bunch of examples of those, and then that will basically be it for the content of the course. I will then introduce the final homework assignment, which will be a kind of a pen and paper assignment in which you're going to do some of these transformations. You're going to start with a regular expression and then transform it into a table, transfer the NFA table, and then into a DFA table, and then a final DFA diagram. And then from there, we've got a few extra days where we have nothing planned. And so we'll figure out what to do. We'll talk more about that on Monday, about what we can fill up the rest of the semester with as far as some content. But it'll be hopefully some things that are interesting, like, and we might, I don't know, we might do some more graph algorithms. Might talk about quantum computing, which is a really popular topic these days. We might talk about, I don't know. We'll figure it out. We got a few days in there. And then the final week of the semester, week number 16, which is coming up, I think, in 3 weeks, that'll be completely filled up with one-on-one Zoom meetings with each one of my students, and we'll talk about what your final grade for the course will be based upon the content that you've done. So I would say if you're a little behind on doing some of the assignments, take the next couple of weeks to try to catch up. Please don't try to cram it all in to the last week, not only for yourself, because you're doing a lot of work during the last couple of weeks, but also for me, because I have to go and I have to look at all of the stuff that you turned in before we finally meet. And so that's a lot of work on my end. So if you could please get those in as soon as you can so that I can get them back to you, again, as soon as I can, that'll make life much easier for both of us. Okay, so why don't I say goodbye to the folks on Zoom, and I'll hope that you have a good weekend and get started on this assignment as soon as you can and wrap up all the others that are still sitting out there in your to-do list. So have a great day. Be safe. Be well. Talk to you later. Bye-bye. And the YouTube folks, again, I haven't heard from you in now like almost an hour. So I wonder what happened to you. Are you still there? So since nobody seems to be commenting, I will say goodbye to you as well. So have a great weekend. I hope you all be well, be safe, enjoy the weather. Oh, Lord Milbury says he's still there. Good to see you. Well, then why don't you have a great weekend. Actually, hopefully, maybe I'll see you tomorrow on my Tuesday, Thursday stream. Starting on computer networking. That'll be fun. All right, take care. Have a great day. Get some rest. Bye-bye.